Okay. Hello everyone. This is the problem-solving session for the second Cubical Agda exercise sheet. I'm gonna share my screen and all right. Yeah. So trying to do this as interactively as possible. So don't hesitate to unmute yourself and suggest solutions or proofs. But you can also write in the chat if you want. Opening the chat now. Okay. So there was a question about the latest Agda lecture on YouTube. Is that the one from yesterday? I haven't checked. Maybe it's not online yet, but we have the lecture notes, so we'll be fine. Okay, so let's start with I'm gonna read over from the exercise sheet. Okay. All right, maybe we can pull up the definition of J. So this is alt period Agda will complain. All right. So this is some sort of subst, and we also saw that. Maybe we can click our way through this. So this is some instance of subst, which is sort of substitution. That's some specific kind of transport, and transport already is defined through this this primitive transp by fixing an I0 here. So what we also going to put this here. So what we ultimately do is we sort of transport something, namely this D here, along family P over the path referral. And this is then equal to D because transporting along referral here is equal to the original element. So what we're gonna actually prove is a little lemma called transport ref. So and I'm gonna make this yeah. So maybe yeah, sorry. No, we already have that somewhere. Yeah. Okay, so transport reference says that all a transport reference A equals A. Oh, it is actually in the lecture notes. Oh, I didn't remember that. Did Anders do that in the lecture? Maybe you remember. Write in the chat. I can, maybe the live transcript is no. Okay, if you don't, we can do this real quick, maybe. So if we type Control U, Control U, Control C, Control comma, then we get the normalized goal, right? And we sort of use, I can go to the goal buffer, make it a bit bigger. Here we go. So we can, so this transp has a special computational behavior depending on this I0. In particular, if this argument is 1, then this will actually judgmentally compute to A. So when we construct our path and transport reference, we sort of go through this. So we vary in this argument actually. So this is something very, yeah, it's like a very technical construction maybe. So we have the boundaries, and what we want is transp figure this out first. No, it's some yellow. Right. Yeah, so the idea is that that sort of, if I is I0, then this transport will just be this transport, and if it's 1, then it will be A. But now we have to give the A like this. Then yeah. Okay. Right. So that was quick. So now we want to construct a path like, oh, yeah, yeah, the use of the for all. Well, this is actually just syntactic sugar. So this is really just the same as this. Yeah, maybe it wasn't the best idea to put it here. I tried to only put it in front of sort of pi types when when the goal, or when like the codomain is a proposition or an H-prop, in the sense that we talked about in the lecture yesterday, because then it really is a for all statement, or should be read as such. Which of course, in this case, unless A is a set, this won't be a proposition. So yeah, maybe this wasn't the best use of it, but now let's see how it goes. Okay. Okay. Yeah. Yeah, so this exercise sheet, I think all the stuff is taken from the prelude of the Cubical Agda library. And it's sort of very hard to motivate how sort of the primitives is set up, like this transp accepting an additional interval argument here, without really going into the nitty-gritty details of how you set up a proof assistant for a cubical type theory. So I'll try, in particular, the way transport is done is to support higher inductive types in cubical Agda, but it also makes it nice to prove these basic lemmas. This would work a bit differently if you work on a different cubical type theory. So yeah, and sort of the mystery of the interval. People writing about this in the chat. This has to do with what a model of type theory looks like in cubical sets. So in particular, we had these primitives. Maybe I can say something about it, because if you want to model cubical type theory, or if you want to, okay, let's put it that way. If you want to model type theory in cubical sets, in a way that gives you univalence and high inductive types, then you need sort of these primitives transport and hcomp to prop up in some way or another, in order to give you enough structure to define path composition and these kind of things. The problem is, well, when you start by defining paths as functions out of the interval that match up on the endpoints, basically. Then you need to prove that sort of your basic types, like natural numbers and stuff, basic data types, they have transp and hcomps. And then all the type formers like pi, sigma, they sort of preserve transp and hcomps or structures of those. And one big problem is that the interval itself does not have a transport or an hcomp. It's sort of like on a lower level. And that's why it's sort of not normal type in your type theory. But it has to be around in some way or another. And I think if you actually look at the literature, if you actually look at the literature, they're very careful with like distinguishing between interval variables or interval variable declarations and contexts and stuff through the normal. And this is swept a bit under the rug in Cubical Agda, and that's maybe why it's so mysterious. So one question was, is the interval an S set? That's an implementation question, and I'm not very good with those. I don't know, actually. Ask Anders or Amy, or one of the people more knowledgeable in that. Oh yeah, now the last question was about the implementation of Cubical Agda, so which is implementing a proof assistant for a special cubical type theory, and there's of course like many details to be worked out. But yeah, maybe we're going a bit off far off the. Yeah, you can maybe look at the exercises and then discuss some pointers of literature if people want to read up on it. I do realize it's sort of hard to get what is going on if you don't have like an intuition for transports and HComs. Okay, let's do this guy though. Let's yeah. So I normalize this term. Right, and this becomes a transport. And sort of notice that this family doesn't depend on I. So this is P, X, and then Raffle at X. So this is sort of constant family, much like in our transport Raffle. And the I0 here. So yeah, we can actually prove this as transport Raffle. Okay. Maybe more questions about that? Or... No. Okay, we can move on. Why does Raffle work? Where? Oh, in transport Raffle. Yeah. So
my question is, why can we use transport Raffle in JRaffle?
okay.
Why is the left-hand side equal to transport of Raffle there? It's not at all obvious to me.
No, yeah. No, it's not at all obvious, but it really like you've actually just look at how subs is defined. So subs is a transport and transport is a trans, and then everything actually computes to this constant family P X Raffle. This is one of the nice, like if you write it out very carefully, you can sort of see why it has to be that. But in this case, we don't have to do the work. Cubical Agda does it for us. It normalizes it and then arrives at some constant family. You can also think about, so P is a family. It takes two or sort of what J does, let's put it that way maybe. What J does, if you take, so J of P and D, so you take that fixed, it sort of gives you a function from which point? From P of one endpoint from Raffle to P of the other endpoint and over the path P, right? So if this P is Raffle, then this will actually, J will actually be a function. So let's put it that way. J, P, D, Raffle is a function from Px Raffle to Px Raffle. And then if you look at how it's defined, it's some sort of substitution along the path here. But this is Raffle, right? So you're substituting.
But it's not a substitution along the path. It's a substitution along is contour single something something right. something.
But this path sort of, yeah.
So I assume this answer is that
here.
when you put Raffle in P there, then is contour single will be definitionally equal to REFL.
Yeah, you'd expect that, yeah. Yeah. And yeah, exactly. I think it boils down to that, actually. Yes. And then you can use transport REFL. Okay. Let's maybe move on. This is exercise 2. Yeah. And I think, okay, so sort of maybe you've seen this in the pop track or in dance lectures, that sort of you have a notion of dependent path and you just show that this is sort of equivalent to the path type where the first argument gets transported. Here, of course, we have the path P as our dependent path. And yeah, we want to show that there is a function in this direction. Okay. So let's see what the goal is, or the boundary. Maybe you use the comma. Yeah, okay. That's better. So we have this guy here again. And again, the idea is sort of we vary this argument. And if this is 1, then this will be sort of x. And if it's 0, we get to the desired thing. So transfer, and then maybe leave a question mark here for what the family will be. And then we want to put the I here and X there. Okay, let's try it, refine. I'm wondering if, shouldn't this be the other way around? Because if I is 1, then this is 0. Wait. I'm also doing something stupid here, I think. Yeah, sorry. All right, I got confused. Maybe you have a suggestion. Of course, we want to.
Isn't this the transport field function from the lecture library?
Oh, do we prove a lemma about let's go there, Control S, search, what's it called? Transport field. Yeah, this looks very useful. Thank you.
But I think then we need to compose it with something else, because it doesn't tell us that it's exactly y, it tells us that it's field.
Yeah, exactly. But we can look at it a bit. So this gives us a it at least helps us with the idea, I guess. So this gives us a path from, or a dependent path from A to the transport, right? So what we can do is sort of that's how I'm thinking how to put this in nice, but yeah, sort of we transport over this family this first component, but what we actually gonna transport is sort of the path p type here. Did that help? Yeah, let's make a drawing. So we only have, okay. This is a bit hard because this is sort of let's say we have trans along A of X, and we want something into Y, right? We have X here, and we have something which is a dependent path. Maybe I can that's something like right, and then transport transport fill gives us something going up here. And yeah, some people saying so this side is then of course REFL. Some people use it saying they're using something else. They're not using transport fill, but sort of a similar idea. Yeah, so this is just one transp that looks very similar. Yeah, if anyone has a suggestion, or yeah. Yeah, it's kind of hard to, if you see it, it's maybe we can do something like let's put it this way. What transport filler gives us is sort of a a line in types, and it goes from this guy to this guy, right? So what it gives, maybe we, okay, I'll try something different. I'll try a different solution here. So we want to transport the P here to this guy over sort of this line, right? So this will be a transport, and then this will be lambda I, right, to something of P. And now we have to look at what the, oh, it doesn't give you the nice boundaries. Well, it does. It says one, it has to be the transport, and the other thing has to be something else. But this will be some sort of path P type. Between something over some family and Y. Right. And yeah. So this guy, this should be the endpoint, which is X in one case and transport along this guy in the other. I'm not sure if this is actually going to work. Yeah. So this, I think this should be the transport fill, no? Of P and X. No. Okay, it doesn't let us. Yeah. Oh no, wait, is it A? No. A is not the right type.
Wait, isn't that just P of I?
You want to put P of I here, but this will go to.
Because then on the right side, at the right end, P of I1 is in A of I1, so we can have a
but then we get a
homogeneous equality.
Then we get a path from Y to Y. We want one from here to this guy.
Oh, right, so we want to transport X, but only I much.
Yeah.
I think it might be easier to just use transport
Yeah.
instead
Yeah.
of
I
combining.
thought this would be a nice solution, but yeah, I think it might not work. It might be sort of clearer, or like easier to motivate, but yeah. Okay, let's losing a lot of time here. Yeah. Okay. Let's do a big transp. This is going to be one of these scary transps. Where yeah. Okay. You can just find. So the last one has to be this family applied at I0, right? And this one has to be an interval variable in I. And we sort of want to vary here with I. That's what I said earlier. Yeah, I confused myself. So when I is 1, then this should just compute to sort of this when wait no when yeah let's do the drawing. So we have the I and the so we fix an I here, let's say. Sort of maybe this is where the drawing can help. We fix some I. This is where our I is, right? So we at some point P of I, somewhere in between here. And then we sort of want to transport it over to here, such that it becomes this thing if I is 0 and this thing if I is 1, right? So we have this scary looking transport, and what we basically do is we transport sort of this path P along something that's very similar to the filler. And if I is 1, then this should just compute to whatever is down here to this family at 0. So yeah, but maybe we can start here. Oh, someone got it to work with transport fill. I would be interested to see this. But this is the base point, right? So this is P of I. This is the base point. This is here, this point here, right? This is P of I. And then over some family, so this would be a lambda J, and this has to be I something. So if I is 1, this will just compute to P of I. If I is 0, this transp will just be a normal transport. And P of 0 will of course be X, right? So this is almost what we want here. We just have to make sure that this will then just be this should just then be J here. That was when I was 0, right? So this should be okay. Okay, so let's look at it again. If I is 0, then this will be transp over I0. So this will be just the normal transport. P of I will be X. So this will be transporting X along this family, but this is 0. So this will just be J. So this will actually be this element. If I is 1, then transp I1 will just be whatever this is. So this will be P of 1. So this will be Y. Yeah. And that's why this works. I have to admit, this is, yeah, I don't know. I still find that kind of magical. Someone got the transpiller to work. Yeah, so this is what I tried to do. So maybe we can give it a prime here. Sign and indent. Wait, okay. Yeah. Okay, let's see. So this is sort of, yeah, what I had in mind. So if you transport P from over sort of some path P family at to this path type, right? Along transport filler. So this will be transporting along the family that is path P's of something, and then from some element to y. So this y stays, this is sort of this column, this stays constant, right? The path P has to be such that if I is 1, then it will just be a normal path type. That means this has to be constant, namely this has to become A of I1, which we can see it does. And this argument is sort of the transport filler going from X to transp. Yeah, very good. Nice, thanks. I think this one is maybe a bit easier to understand with the drawing. This, yeah, than the magical solution. Okay, let's move on. Next one got 3 stars, and it's the opposite direction. Okay. Okay, let's do this. Or maybe we can, yeah, it's worse performance. Yeah, so this is, I think this is probably the same proof in the Cubical library, and a lot of this is very optimized, but you know, I think this is sort of nicer to understand what is, yeah. Okay, I'm looking at the exercises. Maybe so. Oh, okay, they're all building on top of each other. Yeah, 2 path P is actually, yeah, okay, we'll just move on in order. Exercise 3. Oh, wow, we're fast today, but I think it's sort of good to copy everything. Yeah, we already got some help with what to do here, and we're going to copy this diagram maybe. Yeah, I mean, I think with this way it sort of works just the other way around, no? But yeah, this becomes an H comp then. So now P is some path in here, and we want a dependent path. So maybe we can stop. Yeah. Yeah, I think it got 3 stars because it's an H comp, and that's scary. Okay, so the boundaries are actually very simple. yeah, which I guess tells, so we want to sort of close this lid here from x to y, and this is I direction. So if I equals to 0, this should just be reffle, right? If p of I equals to 1, this should just be, if I equals to 1, this should just be, well, this is then the j direction, so p of j. And yeah. And then the bottom, so yeah. Okay, we look at the so we have to provide something in a of I0. This is where this guy lives, but yeah, with the diagram, it sort of tells us where it is, right? This is x, and this is something in a of I1. Yeah, again, maybe do it like this, and the dimensions are so this is I, and this is j. Right, so this will be p of j. Yeah. Okay, and now the bottom is our transfill. Yeah, so this will be something in AI, but yeah, this should be transport fill. Where you can copy this guy in. Lambda, it's nice. Yeah. Okay. So people are saying, yeah, transport is scarier than HComp. Yeah, maybe in a sense, because these things are, in particular, this transp, right? If you're only using the transport you're used to, then maybe it's fine. It's what you're used to from hot. But yeah, but you can do some crazy stuff with the transp. Okay. Using this, we can do exercise 4. Okay. Anyone got a suggestion?
Sorry, I couldn't find the raise hand button, but I have a question for the previous stuff, for the transport versus the HComp.
Yeah.
So what I noticed is, so I understand that HComp is really useful if we have 3 sides set, and the first one is something that we just want to get, but we don't really care what exactly it is, because it's going to be given to us by HComp. Is that right?
Yes, exactly.
But okay, but so then my question is, but so when we did the transp proof of from path P, that seemed like we had all 4 sides like predetermined. Is that right? Or
yes. So this is the difference. I mean, maybe you can prove this with an H-comp. Should we try? Like a prime version here. So yeah, we want the lid here. And we have the three other sides. This is sort of, I mean, this is a very similar square, just sort of flipped, right? So yeah, you should be able to write this as an H-comp. And then this will be lambda, right. I don't know how to, never know how to pattern match here automatically. And this guy at I1. So if this is I0, right, this has to be the at I0, this has to be the transport fill. But now we sort of twist it in the direction. So this is J. No, actually not. Okay, so it's not that easy. Okay. Why?
I think it's just flipped, no? Like it's transport field at sim I or whatever we call tilde I.
Is it like here, you mean? No. Because, yeah.
No, I mean like on the left hand side, but it's flipped, so
Yeah,
it's going against I.
Yeah, right. No?
No, but I, not J, I.
Wait, what do we? This family, you transport over the flipped family. Is that what? Yeah. No. Ah. Is this also flipped? Yeah, okay, this seems to be, I'm not sure if this is possible. Because the problem is this is...
Isn't the problem that it's not homogeneous, so it's a comp, not an H comp?
Yeah, I think that's it, actually. Because the lid is not... yeah, and then this is something else entirely. Okay, let's let's ignore that. Yeah. Yeah, I'm not gonna. Yeah, I forgot the syntax for comp. I'm not gonna do that. Yeah. Yeah, the problem here was that sort of this side was not in one, like this was dependent, right? And this gave us the trouble. Okay. Because as we see here, at each side, you sort of, yeah, you just have a normal path. Yeah, comp is H is comp defined in, look at it. No, it's a primitive as well. And it takes this sort of partial element here. Yeah, exactly. This is now the inner workings of like how it reduces over things. Yeah. Okay, let's not get into this. Let's prove this guy. Any suggestions?
Start with the suggestion from the.
Oh yeah, wait, what's the?
Oh wait, no. Oh, are there more questions? Is there question 5 now?
Oh no, yeah. Question 4 says use 2 path P.
Yeah, so start with that.
Yeah, exactly. Sorry, I didn't see the hint. I had the check window. Oops. So yeah. And now, this is a very, there's a suggestion in here, but I think it should be easier than that actually. Because I mean now, so this guy is a path in. Okay, it doesn't show. Well, it's a path in AI1, right? But every AI is a proposition, so is AI1. So PI0 gives us a right. We want I1, right? This is a proposition, and so it gives us a path between anything we put in here, and actually Agda can figure out what this has to be. Well, modulo some yellow. Right, so this is the transport. I guess I have to bring the A into. And this will just be, no.
If you replace the whole thing with underscore, it will work. Or I mean, not the whole thing, but like to transport.
Yeah, the whole transport with underscore.
Yeah, that works.
Yeah. Then Agda can figure it out if we write transfer at some. Yeah, right. So P of I1 gives us a proof that whatever this transport is that of A0 that we get from the 2 path P is equal to A1. Yeah. Okay. And then I guess using this, we can do exercise 5.
That exercise didn't exist when I started solving.
Oh, okay, yeah. But I think it should be pretty much a consequence of exercise 4. And what we did on the last sheet that tells us that we had this, I think what we had on the last sheet is that to get a proof in here, it's enough to have a proof of a path between the first components and then a path P over this of the second components, right? Oh, yeah. I don't know if you guys remember. Maybe I can bring it up. Oh yeah, that's why solution 7 is important. what was it? Oh, damn it. Okay, maybe we can just remember. What was it? Sigma path P. Yeah. Okay, and now we can refine. So we have to do two things. We have to give a proof that the first projections are equal. Well, no, that we just give it. And then the path P over this, and this is just going to be a dilemma. Okay, this needs three things, and I think it can figure out most. Oh, those are the endpoints, of course. Those it can figure out for sure. This will just be, those are the two second projections, right, of U and B. Now proof that, yeah. So this will be lambda I, and then the B of P of I is a proposition. So this will be H of P of I. Oh, okay. All right. We're looking on time. Right. Are there any questions about this one? Okay, let's do the last one. I think this is might have to do some drawing here. I have to charge my laptop. Yeah. Yeah. Right. So again, this will be a pair such that yeah, in the first projection it goes down to C1 or C0. And yeah, maybe a suggestion of how we get that.
So
H1 and H2 composed together should give us that, right?
Yeah. Let's, yeah, so this will be, let's do maybe like this. This will be C1 and then a J. Yeah. Is that clear? So H0 is the proof that everything else is equal to C0, right? So if we plug in C1, we get a proof from C0 to C1 and then a J. So yeah, this gives us the desired path. And then this is the really tricky part. And yeah, so let's just refine. and we look at the constraints. And we got 4 of them. Right, so this will be a square. Let's draw it. What does it look like?
Well, we see that it's h1y and h0y on two
Yeah,
opposing sides, not the easy one, I guess.
yeah. Yeah, that's okay. That's, I think the directions are, so this is if j equals 1, right, but j is now what I would usually call I, so it's yeah, that's it. So it should be here.
But if j equals 0 and j equals 1, isn't that like the top and the bottom of the diagram?
No, I think it's left and right because j is the first variable. This will be h1 y I. I think we can do it like this, no worries. And this guy is h0 I. And then this guy at I1, oh, this is just y. So this is just reference, right? And at I0, this is h0 c j. So this will be right. This is also, maybe we can fill in all the details here. So this will be, what was it, C0, right? C1. This is also C1. Okay, so now we're filling like a proper square, because what is different to what was done earlier is that we sort of have all 4 sides specified, right? So yeah, so this is not the situation where we have to where we have 3 sides and then we get the top one by hcomp, but this is where we have a complete square and we don't know what should be in there. But again, this this, like a square, is of course just the top side of a three-dimensional cube, right? So this will be one big H comp, and we have to introduce another variable, k. Okay. Let's see. So this will be lambda. Okay, or maybe we can write it. Okay, and then we have I equals I0 to do something here. And we have 4 cases because we have the step 4, yeah. So we have I equals I1, then we have J equals I0, J equals I1. Oh, let's maybe put this here, and then sort of align. And we have the bottom. Okay, so for example, if I equals I0, this is this here, this guy, we have to sort of find a square here. And now this will be something of k. You have to sort of imagine this square being sort of the lid, and then this is one side, it's yeah, orthogonal to it. So this is a new direction. You have to sort of think of it like twist it by 90 degrees. Into something that we can fill, of course. Yeah. Right. Any suggestions? Can I give you, maybe I give you a hint what the endpoints will be. Um, And this will be,
Oh, that's like the last unit of composition. I mean, the last unit of, of transitivity.
yeah, I mean, we can, oops, sorry. Maybe give it, this is goal 0 here, right? No, wait, no, this will be a square. Right, goal 0 will be the square in here, right? Pillar for this square. So we know what this guy will be Raffle, and this guy will be this guy as well, right?
Yeah, that's what I mean. So we're using the fact that referral trans P is P. So if we choose H0 C1 as P, then the bottom, well, I guess the front square is, yeah.
It's actually easier.
Oh.
Yeah, it's a very easy square. It's really just right. It's X here. Y here, and then can I just, no, that's not working. Yeah, but this is Raffle and Raffle there. No, wait. X, sorry. This is X. So this is this square really, right? And this one has a very easy filler. Or someone posted a link, maybe a drawing. Yeah.
Yeah, I posted a link to Quiver
Yeah,
since
yeah.
it's kind of easier to draw in that than in
Yeah.
a sketch.
Yeah. Yeah. Oh yeah, this looks really nice. Yeah, maybe I can share this instead. Or I can wait, let's just do this. Yeah, you can all maybe okay. I'm gonna give you the answer here. This is the first square. This is this guy. And I think I mean, this is actually not the general solution of this guy. This guy just corresponds to one of the connections on the interval. I think this is also just the union, right? Or the join. Yeah. No. Sorry. All right. Right.
But it is.
Yeah. Yeah, this is actually, yeah, not quite, yeah. Because we fixed it, we have the J here fixed, so we have to from out there, yeah. Oh, is it the meat?
Yeah.
Yeah. Sorry. Yeah, very nice. Okay. Maybe we can do, and maybe so with these things, like, you have to be clever. You sort of now have to come up with 4 squares, right? We did the first one. Now it's one that corresponds to this side, then one up here, and one up here. Maybe I can share and go to the drawing board. All right, now you can see this. So we filled this guy, and we figured out that this has to be so this became C0, as did this, and yeah. So we've done this. One of the next problems is maybe figuring out what those 2 guys are, and then we can figure out the bottom. And one of the first things you always try when you prove a you can draw arrows between arrows to show the sides, yeah. One of the first things you try with a cube like this is actually make the bottom sort of, oh, how do I go back? Make the bottom raffle, right? So we want to try to do a square where and now I can do an arrow to another one.
To draw a new arrow, you just click and drag between things.
Oh wow. Yeah. And this gets a label, I guess. So
you write the label in the bottom. You see the black
yeah,
thing in the bottom there.
So this was H0 of what do we have? H0 C1 and then J wedge. Okay, right. Can we click LaTeX? No.
Escape to get back.
Okay. Yeah. Okay, it shows it correctly. Yeah. And right. So we want all of these guys to be raffle. For the reason that we have because we have one complicated square, we have one very easy square. We know how to fill this one where all the sides are raffle, because this is just C0 everywhere, and then we just have to fill the 4 squares around here. So maybe we can do maybe this guy is easy, because we go from raffle to raffle along what is I can
maybe one of the
Oh, because so C0 to Y, we have that, right? Because that's one of
yeah.
That's H0 of Y.
Yeah, exactly. This one is the easiest, maybe.
and use parentheses or
I
backslash
guess I
space.
can, yeah. Can I use this like LaTeX commands?
I think so.
Yeah. At K.
You need another slash comma.
Oh, okay. I mean, it's maybe a bigger one, but yeah. Use it here. Backslash semicolon. Oh. Yeah. This one was easy. How about this one? Maybe we can move this inwards. So again, sort of, maybe we can first, so this is Reffel, this is Reffel, this is H0 of Y. And this, of course, should also be H0 of Y, right? So this is the same as this, but only with Y here. So this is H0 Y, and then now it's I and K, right? Because this is H0 Y. Okay. And the last, it's maybe the hardest, I guess. Anyone suggestion for that one? You can figure this out. Okay, so we want something. We want something. Yeah. So first of all, C0 to Y, that's H0, right? And Y, C0 to C1, that's got to be an H0 as well. And then from here to here is an H1. So this has to be something of no, wait, an H0 of an H0 of,
Should we do the edges of that side first?
maybe we can write them. This is H0.
So we already fixed that to be H0 C1, right? Because when we were doing the front face.
Yeah. And this is H0 of H0 of Y at K, right? Maybe we can do it like this. This looks very nice. Okay. Wow, wait. So there should be some.
So H0 outermost, I think.
Yeah, I think so too, right? H0, then
H1 of Y and I think. And then finally K.
Yeah. So this would be in parentheses h y and I at k. Yeah, I think that should check out. So if k equals 1, this will just be whatever is there. Yeah. That's good.
And if
I equals 0, this will be this, and then this will just be this. Yeah. Yeah, very nice. Here we can just copy this because this was the okay, I'm gonna go back to share Emacs. Yeah. Yeah, which one? That was this guy, right? So this is j equals 1. This was the hard part. Right. Oops. Oh, I mean, okay, first, okay, let's
No, it's you have j equals I1 twice. I think it's just the. I mean, your third and fourth case is the same.
oh yeah. Oh yeah. Thank you. Yeah. Oops, sorry. Yeah. Okay. Then which part was the easiest? I equals 1, right? That was just h0 of y. Okay. Yeah. And this part was basically the same one, but with y, right? And h1. No, was it? No, it's also wrong here. That's why I was confused. Yeah. So this was a y, and this was an I. And voila. Okay, we did it. Great job. Thanks. Okay, are there any more questions? Oh, Taurus equals Taurus. Yeah, I guess we don't have time for that. I've never tried myself, to be honest. And I think Anders said if you manage to do it, it would be a nice addition to the Cubical library. Yeah, maybe we can take it to the chat another time. We can make office hours. When I have my office hours next year, next week, we can look at it. That could be fun. Okay, if there are no other questions, I'm gonna.
will you add a link to the drawing in the solutions if you're saving?
Yes, that's
You can press save in them to save the updated version.
Yeah.
And
So
then
we
get
save, and then yeah, I'll put a link. Right. Yeah, we can provide it online somehow. Thanks. Yeah, that's a cool idea. I'll send it to Astra. All right. Okay, if there are no other questions, I'll stop the recording.